So welcome to session number 5. In the previous session, we started our discussion on laws of manufacturing. We'll continue with the discussion. If you recall, we start talking about matching demand and supply in a variable and uncertain environment, right? And we gave that example of a dam, right? So to how to match that supply and demand, we need some kind of buffers, and buffer becomes levers to match the demand and supply, right? So I give that example of a control structure like a dam, because rainfall supply is highly uncertain. It comes for a very brief period of time in a year, right? But demand will be more or less constant, right? So you want to match a demand and supply by putting that control structure as a buffer. So the same logic should be applicable in a manufacturing or a services setting, right? And we normally have three kinds of buffer: in inventory buffer, a capacity buffer, and the time buffer, right? So I'll explain that, right? So you can think of maybe a check-in counter at an airport, right? So if you have seen a check-in counter, so there would be at least some 3-4 counters, and in front of those counters, you can actually see a long queue, right? Now, when I say some kind of a buffer, so it means that ideal scenario would be when a passenger comes in, the counter is immediately available, right? But normally that does not happen, right? Because most of the time the passenger arrival will be highly random, right? And even the service time at those counters will also be random, right? Now, what happens is if there is the combination of these randomness, you would see either you have unused capacity, right? So it means happens that for a given period of time, there is not even a single customer arrives, right? So you see those counters empty, right? Or it may happen that a lot of passengers they arrive at the same time, right? So it means that you actually see long queues. So when I say capacity, it means that you have some kind of capacity buffer, right, which may remain unused or unutilized for some time, but that will improve your service levels, right? So as soon as a customer comes in or a passenger comes in, there is a capacity available to serve that passenger. But that's expensive, remember that, right? So capacity is not free, right? So in this case, the machine is, or a server or a check-in counter is waiting, correct? When there is a queue, it means that assume that you have only one check-in counter and there is a long queue in front of that. In that case, the demand is waiting, right? Correct. And in a typical manufacturing process, there is a possibility that something is getting, say, assembled at a particular point, right? And the work in process is actually waiting to get processed at that machine, correct? But the example which I gave, in those cases, the airport example, in those cases, the inventory issue will not come. So either the customer will wait or the capacity will wait, right? But these are examples of buffers to meet the supply or to match the supply and demand, right? In an environment which is variable and uncertain, right? So in this setting, what we actually have to see how technology can actually allow us to reduce the impact of environment in matching the demand and supply, right? So the point I think which comes in, can machine intelligence do that, right? Can machine intelligence, so I'll use AI and machine intelligence maybe synonymously, right? So can machine intelligence allows me to understand the environment better so that I can actually maybe match this demand and supply at a cheaper cost, right? So maybe the roles of buffers becomes limited, right? So that could be in form of multiple ways, right? It can allow me to make a better forecast of the demand, correct? It may allow me to see if there is any constraints or disruptions coming in supply chains, right? So all those possibilities, so it means that I can actually understand that environment better, right? And that allows me to match the demand and supply maybe at a cheaper cost, correct? So with this narrative, I'll continue as the supply chains are becoming more and more complex, right? So I think post 2000, as we have talked about the emergence of supply chains, right? What is happening is the transportation cost, the logistic cost has come down. So you see more trade with more distance player, and I think the whole idea of maybe looking for cheap suppliers, right? So the cost arbitrage comes in, and one of the objective was to make always faster, cheaper, better. So cheaper is, instead of making it here, let me outsource it maybe to some countries like China or even India, right? And you look for cheaper suppliers, and we already have seen the benefit what comes along with the outsourcing in terms of economies of scale and experience curve, right? So the lead times have gone up, right? So the complexity of managing supply chains have gone up, right? More and more variety. So I think we are still not talking about mass personalization, but if I think of variety, I can actually say that even for a toothpaste, you may have multiple variants available, right? So the complexity of the product is actually increasing because in fact you want to personalize the product, right? You can think of a typical automotive, right, example where the technology keeps on increasing. So you see more and more digitization. Now you may be talking about autonomous vehicles, right? So you may have a laser camera which can scan the environment, right? More complexity, so the number of components may keep on increasing, right? And moreover, it's not just about the far distances or variety or complexity. It is also that even the supply chains are becoming more and more long, right? So not just in terms of the distances. So in fact, when 2001 tsunami hit Japan, uh, at that point, companies like Intel, they try to map the risk in their supply chain, right? So they could not go beyond tier 2 or tier 3 because after that the supply chain was highly opaque, right? So can the technology allow us to maybe complexity may remain, but how you actually mitigate the risk which come along with that complexity, right? So I'm going to spend some time on IoT when we talk about technology of the future, right? So, can uh, technology like sensor enabled Internet of Things, right? So, I can actually map what is happening in supply chain, correct? Maybe get that information in a centralized form, maybe a centralized information warehouse where all that information get collated. I can do some kind of computation and find out what is going to happen, right? So all these possibilities will come along with technology. Moreover, I talked about the pipelines to platforms, right? So instead of having dedicated suppliers, so is it possible for me to actually think of supply chains in the form of platforms, right? So I can give you an example of companies like Ariba, right? So they become a procurement platform, right? And can the technology be such that instead of even thinking about organization, I think I mentioned about that, right? So is it possible to just think of whether I need to make this product today and I may not have any supplier, right? Can I just get it on demand? Correct, right? So is it possible? And that can technology be the facilitator in doing that, right? So I'm talking at a very macro level, but this is something which is has been already discussed as part of future. So we have talked about the economies of uh, um, scale. Now I think we are talking about economies of unscale, right? So your organization is unscaled to such an extent that everything, whatever you want, is available on demand, right? And the platform certainly will play that role, correct? So when I talk about Ariba, I'm looking something similar. That in fact, in India we have this government e-marketplace, right? So these are nothing but procurement platforms, right? Which may in the future may be true for manufacturing setting also, that I don't need anything. I have a manufacturing platform where whatever I want should be available, right? So this is something which we are going to discuss as part of this course, right? And the technology behind that. What actually enables that thing, correct? Now, if you recall, we always were looking into that faster, cheaper, better, and diverse. And I think now we are emphasizing more on how you cope up with that complexity, because the products are becoming more and more complex, right? So I still have those four objectives in mind, right? But with increasing complexity, how can I still achieve those four objectives, correct? And I think let me just add, which may be becoming more and more significant these days, is this notion of sustainability, right? So it should not confine just to saying that I am making the faster, cheaper, better, and diverse. It should also be sustainable in the sense of environment, right? So a lot of discussion these days on that you manufacture the product in the in such a manner that it should be easily recyclable, right? So there should be you can reuse it in some form, correct? So in fact, you can think of even the computers which we are using, right? So is it possible to maybe either remanufacture or recycle or reuse, right? So all those possibilities should be part of your manufacturing thinking, right? So it's not just about faster, cheaper, better, and diverse. Let it also be sustainable, correct? So with this, I'll start going slightly into the math side, right? So till this point, our discussion was mainly in terms of the wisdom, right, of manufacturing. So we have seen economies of scale. We may be talking about economies of scale, right? Now, the point here is how you quantify variation, right? So some of you have seen probability theory. So I'm talking given a density function, right, or a probability density function, which is fx, correct? And mu could be the mean value of that function, right? Correct. So it could be anywhere. I've just put some arbitrarily somewhere mu, right? Now, what we want is how you quantify the variation, correct? So this is the typical formula for variance, which says that given the mean, right, how that mass is distributed with respect to that mean, right? So if you have seen say center of gravity or moment of inertia, they actually does the same thing for a rigid body, right? So I can say that mean is nothing but for a given density function, it is nothing but the center of gravity, correct? And so how the mass is distributed with respect to that center of gravity. And you square it just to normalize it, because it could be either side, this side and that side, right? So this is just one measure, or you can say measure of dispersion, right? And it gives me how the mass is distributed, right? So so we go further. I think we don't want to just directly use the formula. The point what we want to use is what wisdom it gives me to cope up with this variability and uncertainty. So I may be again talking about some laws of manufacturing or maybe some laws of nature, right? So if I just talk about maybe a simple mean, right? So I give you some numbers which maybe say assume sampled from this normally distributed some density function, right? But in this case, we are taking a normal density function with the given mean and the variance, right? Now, I sample some numbers from that distribution, correct? And I compute the mean, right? So people who have seen, I can actually call it it's like a sample mean, right? Now, because it's a function of what numbers we sample, it means that x bar itself will not be a constant because I'm just sampling some n numbers, right? So if I do one more round of sampling, I'll get a different x bar, correct? Now you keep on sampling and you will keep on getting different x bars, right? So x bar itself would have a distribution, right? Now, if you see this, if xi is if x size the points have been sampled from a normal distribution, the distribution of x bar, in fact, I'm pretty sure you might have heard about this, the distribution of sample mean would also be normal, right? Because I've taken this as a normal, right? So people have seen CLT, this central limit theorem, that may not be true all the time, right? It is only for large n, I can say that. If this xi would be some arbitrary distribution, that would still be normal, but that is true only when we talk about large n. So that is the concept from the central limit theorem, right? But for time being, I'm just taking xi as normally distributed. So x bar will also be normally distributed with the same mean as the mean of that xi or the distribution of xi, but the variance is lower. You can actually see that. It is sigma square by n, right? So n is the number of points which were sampled from that distribution, right? Now, if n becomes infinity, you can easily see that x bar would not have any variation at all, right? And this wisdom is in fact one going to play a very key role when we talk about matching demand and supply, because it actually gives us some kind of a law. I can call it a law of nature, that if I aggregate, I'm actually reducing the variability, and you can actually see that, right? So x bar is nothing but some kind of an aggregation, right? And aggregation is actually reducing the variability. So this becomes a significant wisdom to match the demand and supply, right? So if it is possible, so even I talked about is it so the question is it possible for us to reduce demand variability, right? So demand is more or less exogenous. I cannot change too much on the demand side, right? So demand comes with its own variation. But is it possible? Can I use some strategies where is it possible for me to actually reduce the variability of demand? Correct. So we will be discussing some of these ideas uh, as part of matching demand and supply strategy, and the same thing should be used in the manufacturing context. Correct. So this wisdom should be there that aggregation reduces variability. It comes with a caveat, right? So for time being, I'm just ignoring that caveat part, right? But for time being, just believe in what it says, that aggregation reduces variability. Correct. Right. So so from quantifying variation, we come to the process parameters, right? So most of these manufacturing systems, we already have talked about the job shop as a manufacturing process. We talked about continuous. We talked about assembly or batch process, right? So all these are processes. So a typical manufacturing process would take some input and give you some output, correct? So manufacturing process could have multiple sub processes also, right? So even I can actually call a factory itself as a process, which could have multiple sub processes, right? Now, there would be some process parameters which can come in the form of an inventory, which represent as I. And I'm talking the inventory within a process, right? So I can call it work in process, right? There would be throughput rate at which the output is made, right? And there is a clock time or sorry, cycle time, which is nothing but the clock time taken in the process, right? So you actually can think of time from this to this, right? Now these are process parameters, right? So there is some kind of relationship between uh, these three process parameters, right? So there would be some relationship between work in process, the rate at which output is made, and the clock time taken in the process, right? So, so if this is clear, let me just start thinking about some laws, right? So the first law which comes, some of you might have seen this in some queuing theory settings, right? Which is called as the Riddle's law. And you can actually see that this paper was published in 1961. And so the notations may be different. So this is inventory, this is the the throughput, right? And this may be the cycle time, correct? Now these notations may be different, right? But the idea is that inventory is equal to the throughput into the cycle time, right? And let me add, this is nothing but you can actually say this is the minimum WPI which you actually need for a given cycle time to maintain the throughput rate of R. Correct? I'll explain what that means, right? Okay. Now, if you see this, there are three settings given, right? And let this be an automotive process, manufacturing process, and these are maybe the work in process, right? Now, let us think of an example where from um, from input to output, there are 10 different sub processes, correct? And let us not bring any variable into that. In fact, if you read more into the Little's law, it is independent of the distribution, right? So there could be a process time, all those things have been averaged out, correct? So in fact, I can call it the average of or you can say minimum of the average WPI is equal to average cycle time and the multiplied by the average throughput, right? Now, there would be 10, say, sub processes, and each process takes, say, 10 minutes, right? So, I put some input here, and so total cycle time is 100 minutes, correct? And let us assume that this particular process produces, say, 240 units per day, and assume that there is only 8-hour shift, right? So in 480 minutes, they produce 240 units, so that is 0.5 per minute, correct? So it means that for this case, R is equal to zero point 0.5, T is equal to 100. So the minimum inventory which or WPI which I need in this case is 50, right? So you can actually see that, right? Now, if So in the first case, you can actually assume that this is 50. In this case, my inventory is more than what actually is needed. Correct. So for the if the cycle time remains 100 minutes and I want the throughput of zero point 0.5, I only need 50 WIP, right? In this case, it is less than 50, so the process may start because you don't have ample inventory, right? If you want to maintain the throughput of zero point 0.5, you should at least have 50, correct? Your system can work beyond 50 also, but that is not needed because in this case you actually have inventory more than what is actually required, right? Correct. Now you can actually take this as a wisdom that if I reduce the cycle time by some means, right? So if you recall, when we moved from the mass production to mass customization, we talked about that reducing the setup time from 1 day to say some minutes, right? Now, if we actually reduce the setup time to such an extent, the cycle time also reduces, correct? In fact, the Ford idea of not having variety was precisely because it does not want changeovers, right? Because the setup time will actually increase the cycle time and that will certainly impact the overall system, right? So in this case, if you see, if by some means I reduce the cycle time, right, the inventory will also get reduced for the same throughput, right? So if instead of 100, say I make it 50 minutes by some means, then in that case I need only 15 to 0.5, only 25 is the minimum WIP needed, right? And remember that this law was not actually given by Littles. He only proved the law. This is a folk law, right? So no one can actually claim that this law was given by this person, right? So this law exists even before this paper by JDC Little, and uh, only thing is he actually proved this in a paper published in 1961 in Operations Research, right? But the wisdom I think should be very clear that it says that what is the minimum WIP needed to have a particular throughput for a given cycle time, right? And by some means, if we reduce by maybe technology or anything, if I reduce the cycle time, in that case, the amount of inventory or whatever WPI will also come down, right? So this is something which is important, and this forms one of the major laws of a manufacturing process, or we can just call it laws of one of the major laws of manufacturing.